We're on. This is Absolute Zero. I am Rachel Appel.
And I'm Bertrand, and today we're talking about
Black holes.
black holes. Yeah.
So these things. So how about I'll do the layman's version of what a black hole is, and then you can tell me how far off I am on this.
That sounds excellent. Let's do that.
All right. So because I watch movies and stuff and read books. So here's my idea of a black hole. It's not an actual hole. It's not even necessarily big. It's a very, very, very dense thing out in outer space. And it happens as the result of a death of a star in which the density is so great that it creates such gravity that light can't even escape. That's about, I think, all I have on it. But they're not actual holes, and I don't even know that they're necessarily black, but it's about the gravity, the light not escaping, and all that stuff, right? Is that even close?
Yeah.
Okay.
There are things that I will have to correct.
Well, I'm sure there's more to it than that. I mean,
Okay, so is it a hole? Well, the general relativity black holes could be seen as a hole in the sense that there is this region of space-time that is causally disconnected from the rest of the universe.
okay.
And the other thing is that if you look at the shape of a black hole, in general relativity, it looks like a tear in space-time. The fabric of space-time is actually torn.
Okay.
And so I would actually describe it as some kind of hole. But
Okay.
then there is a whole zoo of black holes,
Like a
and we'll
crevice,
talk about that.
maybe?
So are they black? So they might be holes. Are they black? Well, as you said, no, not entirely. So the horizon would be black because it's like a one-way membrane.
Right. Well, I watched Interstellar too.
Yeah, which is awesome.
Oh, there's
I
that.
love that movie.
And
I
that black hole
love
is
that
pretty
movie.
spectacular.
And it actually has black holes that are pretty accurately described, because they had Gibson, I think it was Gibson, working on the movie, and he's a world expert on black holes. And some of the visualizations are actually their actual physics simulations. Yeah, so what I was going to say is that even if the horizon itself is black because things can go in but not out, immediately around that horizon there can be some emission of light and other particles. There is the Hawking radiation, and there is also all the stuff that is, well, Hawking radiation is so tenuous that it counts. It's an important phenomenon, but you won't be able to observe it because it will be so faint.
Okay.
But there is all the stuff that is going around the black hole, and that is either just orbiting around it or about to fall into it. And that stuff is actually very, very bright.
Actually, that's how we observe black holes, isn't it? Because we can't just directly look at them, correct?
Yeah, we observe what's going on around them.
Around them, right?
So there are basically two parts about that are interesting and very energetic about what's going on around the black hole. There is the accretion disk, which is all the stuff that is rotating around, and it's a disk because that's a shape that is stable, that is more stable than a cloud or something like that. And this is why planet formation happens in disks as well, why you have rings around planets and so on. And also,
sci-fi picked up on this concept. Sci-fi has picked up on that concept. Yeah.
So there is that, and so this is emitting light because there is friction inside of that accretion disk because there is a difference in velocity between the matter that is at different distances, and a few other phenomena like these. And this is actually emitting X-rays and all kinds of crazy radiation.
Oh, that is interesting. So I saw a headline, like just a news blurb. I didn't even actually get to read it. And it said Stephen Hawking just released some information on, he thinks that black holes might be like a gateway to another dimension or universe.
Yeah. Yeah, well, that's not a new idea.
Oh, okay. I just happened to just see it recently.
Yeah. It is actually an idea you see in about every movie about black holes, whether it's Interstellar or Black Hole from Disney or
the sci-fi. I didn't realize it was an actual.
Yeah, because there are several components in that. One is that in popular imagination, if you have a hole, it must have another side.
You
right?
gotta go through it. Yes.
If something goes through, it must come out somewhere. And
Right.
actually, no, not necessarily.
I don't know. Have you seen a garbage disposal?
Yeah.
That's what they are, though.
Yeah, and we'll talk about singularities and what that means. But okay, so maybe that's a naive reason for having black holes as ways to travel from one place to another. We could talk about wormholes and stuff like that are not exactly black holes, but
yes, that's what I just thought. It was wormholes rather than just black holes.
And there is also the idea that in physics, pretty much everything is time reversible. So if you look at the equations, the fundamental equations of physics, oftentimes you can just reverse time and the equation doesn't change. So it means that if you create the model for a black hole, then you probably also have the model for a white fountain, which is the reverse phenomenon where stuff comes out but cannot go in.
And that's a real thing?
It's a theoretical possibility, but the problem is, how do you form such an object?
Okay. Have we, like...
because a black hole is easy to build. You take a star that is big enough, you wait until it has exhausted its fuel, and it will collapse. And if it's massive enough, it will collapse into a black hole. That's easy.
Okay.
To create something like a white fountain, there is no known mechanism to create that. So
yeah, that sounds okay.
It would have to be fundamental. It would have to come with the universe, which is probably not something that
freebie we didn't get.
Yeah, that doesn't sound very believable.
Right.
But it's a theoretical possibility. Yeah. So I think an interesting question to ask is, how do we know that black holes exist? And do we know that they exist, actually?
Yeah, well, there's supposed to be one in the center of our galaxy, correct?
Yeah, we think there is a supermassive black hole in the center of most galaxies, if not almost all of them. And in the case of our galaxy, I think it's estimated at something like 4-point-something million solar masses. So it's more than 4 times more massive than our sun.
So are they just sitting there gobbling up everything in the center of the galaxies they're in?
Yep.
Yeah, okay. Just like everything's going down the drain, orbiting it.
Yeah.
Yeah, okay.
Yeah, it kind of looks like a drain, that accretion disk that goes around. But in the case of supermassive black holes, I don't know what that would look like, because it would probably be more like a bunch of stars orbiting the black hole, and occasionally one just falls into it. Oh yeah, and the other thing that I wanted to mention about what goes on around a black hole is the jets. And this is one of the ways we can observe what's going on around the black hole, because those are really extremely energetic. So you have, it's just the dynamic of matter rotating around a massive object. I don't know the exact details, but around any sufficiently massive object, if you put matter around and let it rotate and fall into it, you will have some of that matter that will be ejected very, very fast as jets. And you have a pair of those, and there are lots of those that we observe, and they are going very, very fast. Like they are very close to the speed of light. And if you happen to be in the way of one of those, you might be in trouble.
Doesn't sound pleasant.
No, it's not.
So you think I heard Neil deGrasse Tyson once say that if you could hypothetically, say, take a spaceship and just drive out to a black hole and go to the edge, what would happen is you would get sucked into it and you would just get like stretched out.
Yeah, the technical term is spaghettified.
Spaghettified?
Yeah.
That's a cool word. I gotta find out somewhere to use that. I can't even spell it, I don't think.
So what's going on is that when you get near the horizon of a black hole, the tide effect. So you know what a tidal effect is? What the definition is? Okay, so for those who don't know, it's when there is a difference in the gravitational force between 2 points. Okay, so gravitation is more intense closer to the object, and less intense as you go away. If the gravitational field is not very intense, usually that will be smooth, and there will be almost no perceivable effect, except maybe for the seas going up and down twice a day. But if you get into very, very intense gravitational fields, then you will actually be able to feel that effect, where your feet, if you're going into the black hole feet first, your feet will be attracted with a much stronger force than your head, and it will just pull you apart, and it will be so intense that you'll be reduced into some kind of weird spaghetti.
It's something we will never feel on Earth. Without heavy machinery, I suppose, to pull you apart.
Yeah, that doesn't sound very...
That doesn't sound pleasant either.
No, not very. But the interesting thing is that the bigger the black hole, the smaller the effect.
Really?
Yes.
That's interesting. Oh, I know why, right? Is it because it's not as dense as if it's bigger, right? Is that it?
Kind of. It's that if a black hole is very massive, then it's also very big, which means that the horizon is going to be farther away from the center.
Probably not as powerful?
Yeah, well, it's so big that one thing that is useful to know is that the gravitational field around a spherical object and the gravitational field around a black hole of the same mass, those are exactly the same until you reach the surface of the object.
Okay.
So if you have a black hole that has the same mass as the Earth and you're 6,000 kilometers away from it, you will feel the exact same gravitational field as you are feeling right now.
Okay.
There will be no difference. So if you are near a black hole that is very massive, such as the one in Interstellar, actually, you won't feel the tides with such a huge intensity. Now, if you're approaching the horizon of a smaller black hole, so we are talking about an Earth-sized black hole, you would have to get, you would be able to, the horizon would be much smaller, so you would be able to get very, very close, and the gravitational field would be very intense, but it would also be in a smaller region of space, okay? So the differences, the variations from one point to the other would be a lot more intense.
Right.
So you're right in saying that if the black hole is big, when you get near the horizon, those differences are much slower. It varies much on a much larger scale, so you don't feel it as much. So you could actually survive going through an event horizon. Well, you wouldn't be killed by that. You would probably be killed by something else, but not by that.
Choose your poison.
Yeah.
So do we have any kind of effects out in outer space, kind of like when you go to the southern hemisphere and you flush the toilet and the water go their way? Anything like that?
Yeah.
Oh,
So,
really?
yes. Yep.
I had no idea.
So black holes can be in rotation, so they can have an electric charge.
Okay.
They have a mass. They can have an electric charge, and they can have rotation.
Okay.
If the star that formed a black hole was rotating, like most stars are, then it's like the denser.
It's gonna keep rotating, yeah.
No, it's going to rotate usually faster. Well, it will rotate faster than the star. It will keep its momentum, but because it will be smaller, like the denser, folding her arms, we'll start spinning faster. In the same way, a star spinning, forming a black hole, will end up being a black hole rotating a lot faster. And the interesting thing about that is that when you do the calculations in general relativity, there is a phenomenon of frame dragging, where the rotation is actually dragging space around it.
Oh, wow.
So space itself is rotating.
Being dragged. Okay.
That's the thing that's fascinating about black holes. It's that basically the matter is gone, and
that's interesting.
What's left is space-time.
Okay.
But space-time that has the same physical properties as the object that formed the black hole. But the matter is gone.
That's interesting.
And space-time remains. And one of the things about rotating space-time is that it can drag objects around. So, and space-time itself is dragged around in this way.
Interesting.
So yeah, you have that toilet bowl effect.
So do black holes ever go away? Do they die? Like, so we know the star dies, that forms the black hole. Does the black hole itself ever die and turn into something else? Does it just go away? Does it end up eating everything in its path for the rest of eternity?
Because that horizon goes only in one direction, and stuff cannot escape from a black hole. Until recently, we thought that a black hole would only grow bigger. And then Stephen Hawking discovered that if you add quantum mechanics into the mix, then what can happen is that, so you are near the horizon, and you know how in a vacuum there are pairs of particles and antiparticles that are being created and destroyed all the time. And we call them virtual because you can't really observe them. You can only you do actually observe their effects, but they are almost like something we use in calculations, but that doesn't really exist, except in very specific situations. So that specific situation is when you have a pair of particle and antiparticle being created near the horizon, and one of them goes inside and the other escapes.
Okay.
And in that case, well, the half of the pair is gone, and the other can actually be observed and everything. So, and that borrows some energy from the black hole, and that takes away energy from the black hole. So in usual circumstances, the stuff that falls into the black hole would feed it much faster than the black hole would lose energy and mass through that virtual particle effect. So usually a black hole will grow, but if you look at very, very long periods of time, if you look at what will happen to our universe in hundreds of billions of years and more, then those effects, in theory, are going to become dominant.
Okay.
And eventually those black holes are going to evaporate.
Oh, okay.
And the smaller they are, the faster they evaporate.
That's all right.
And if you could, for example, if you could form a black hole that has the mass of, I don't know, an atom, for example, it would evaporate so fast that you wouldn't even have time to observe it.
Do you think then that happens a lot? There's that size black holes, that tiny, maybe near us?
We don't know. We might be able to detect the radiation signature of something like that happening. But for the moment, we don't know. We don't think so, because there are other considerations that make them theoretically unlikely because of conservation laws and stuff like that. But they might. We might see them one day. But yep.
Good enough. Okay.
Yeah. So. Yeah. So how do we know that they exist? And do we know that they exist? That's
we observe the stuff around them.
Yes.
But
so we observe objects that have all the characteristics of objects that have the density of a black hole. So, for example, in the center of the galaxy, we see stars going around that object that seems to be very, very massive. But yeah, we know that there cannot be a star that big, and we would see it, and we don't see the object, and stuff is rotating around it in a way that is consistent with an object of millions of solar masses in there. So yeah, there is something there.
And we can't see it because the light's not escaping.
Yeah, so we also see X-rays coming from sources that look very much like what would happen around a black hole. And the latest, most compelling piece of evidence that we have for black holes is when we detected the gravitational waves from, we think, two black holes colliding. We talked about that on our first show. And that might be the most direct observation that we have of black holes. And we can look at the signature of those waves and infer a lot of properties of the objects that we are looking at. It corresponds to how we think black holes would behave. But they are still, in a lot of ways, they are theoretical objects, in that, okay, we know that there is something very dense there.
Right, and we've never directly observed them. That's all the indirect observation.
Yeah, and
science is full of that, and we do have good methods to do it.
Yeah, but because we will never be able to look inside, by definition.
I don't know. Did you see Interstellar?
Right.
Matthew McConaughey, or maybe Matt Damon will go get stuck in a black hole, and we'll have to retrieve him one day.
Yeah.
I'm pretty sure that's actually going to happen at some point. Gonna have to get Matt Damon out of a black hole. Got to save him from everywhere.
Yeah, that guy, we always have to save him. It's amazing. But more seriously, the whole movie is based on the idea that if we could manipulate gravitation the same way we manipulate electricity and electromagnetism, a lot of things would become possible that are very hard to predict.
It's be like a set of Marvel super characters if we could do this.
Yeah, it's the idea that sufficiently advanced technology is indistinguishable from magic.
Yes.
So who knows what we would be able to do if we could if we could control gravitation.
That'd be awesome. It so sounds like it's out of like DC Comics or something.
Yeah,
it really
because
does.
yeah, gravitation is pretty much space-time.
Yep.
It's the geometry of space-time. So you would be manipulating space and time, and with all of that, all that is implied by that. So who knows?
Cool.
Yeah, yeah.
Any other
and
yeah,
yeah. So the reason why I'm interested in asking that question, do we know that black holes exist, is that we know so little about the physics that that would apply to those conditions, those extreme conditions, that we actually don't know that much. And so the horizon is actually not that extreme. What is really extreme is that singularity that is supposed to be at the center of a black hole. But even on the horizon, there are a lot of things that we don't know. There are models that predict that you would have a firewall. So when you approach a black hole, you would see very, very high energies, and that would actually, in some cases, diverge to infinity. So there are a lot of theoretical problems associated with black holes. And basically what that means is, okay, physics is broken in these environments.
Okay, at least it's in those environments, because I go on airplanes and stuff like that.
Yeah,
physics working down here, quite frankly.
Yeah, it works fine most of the time, but there are a few places in the universe where our physics clearly doesn't apply.
Right.
And we have a hole in our knowledge, a big gaping black hole, and those places are the Big Bang and black holes.
So has anybody do they say things like black holes are almost like mini Big Bangs because it's the death of a star, or do people put it that way ever, or is that just not even close to base?
So there are real differences between the universe and the black hole. But if you said that the universe is a black hole, you would be right in a number of ways.
Okay, yeah.
There are interesting similarities between the two. Obviously, we don't feel like we're in a black hole, but there are a lot of characteristics that are common between the two. Yep.
Cool. Interesting. It's really heady stuff. There's a lot of very abstract concepts when you're talking about this, and giant numbers and giant distances that we don't tend to deal with on Earth a lot. So,
yeah, and
we grapple with for most people, I think, if you don't work in that area.
Yeah, most of the difficulty is that in our everyday experience, we have objects in space.
Yeah, our everyday experience is not even close to what's out.
And then you have time, which is some
different
other dimension that we don't consider as an object. We consider that we are in time and we are in space.
Right.
We don't consider time and space to be objects usually, because it's not useful to do that. But when you look at the Big Bang or when you look at a black hole, you have to, because nothing makes sense otherwise. And yeah, a black hole bends time and space. This is how it's possible that the horizon is that place where time flows only inwards. So it's like time flows in space or something like that. So, yeah, it's complicated, and the way why our physics breaks is that Okay, so when you look at quantum mechanics, we know fairly well how to do quantum mechanics in flat space, in space that doesn't behave too weirdly. The problem is that general relativity tells us that space-time tells matter how to move, and matter tells space-time how to bend.
Okay.
So the density of matter and the way matter moves, the way the energy and momentum of matter is distributed,
Interdependent.
this is what determines the geometry of space-time.
Okay.
And then in turn, the geometry of space-time, constrains how matter moves. So where was I going with that? Yeah. So if that is the case, then, and that is the case definitely, then those quantum particles, the quantum mechanics of particles also has to have an effect on space-time. Because all matter is quantum. So you can't ignore quantum mechanics. There has to be, the quantum nature of matter has to propagate to space-time. Okay. So space-time has to be quantified because space-time is influenced by matter. So you will have to marry the two, but the problem is that there are some fundamental difficulties in doing that. Okay. And those are mostly mathematical problems that would be way too complicated to explain here.
Yeah, I'm pretty sure the math is over my head at that level. To say, yeah.
Yeah, but basically, if you try to do it, what will happen is that space-time will pretty much boil. Okay. And it will start acting like a foam that just goes.
Space foam.
Yeah.
That would be interesting.
And so there are a few attempts to reconcile the two. Well, quite a few. There are thousands of physicists working on that stuff. And some of them are actually making space-time discrete in the sense that it's not continuous. And you have superstrings that are also another attempt, but that means that you would have some extra dimensions and so on. Complicated stuff, difficult to verify, and so we are. Yeah. It's interesting to do physics.
Yeah, and it's hard to be able to observe these things directly.
Yeah, because they are so high energy that they are out of reach right now.
So do all stars end up being black holes at some point?
No. That's a great question.
So there's different kind of stars. Is it like red dwarfs or a certain type that does it? Is it just the length that they're alive, just when they die? Like, how does that work?
So the way a star maintains itself is that there is this fight between the inward tendency to collapse under its own gravitation and the outward forces that are caused by the nuclear reactions going on that create energy that just push everything out.
Okay.
So there is an equilibrium between the two, and in its normal lifetime, as long as there is fuel, the star will be mostly stable. Once it has exhausted all of its fuel, then that outward pressure disappears and the star collapses. So a few things can happen. First, new nuclear reactions can start. So a new star that began from a cloud of hydrogen would start burning its hydrogen first, and then that will create some heavier atoms.
Okay.
And those heavier atoms might not immediately start creating other fusion reactions. But when the star has exhausted its hydrogen, then it will collapse, and that collapse might result in other fusion reactions beginning.
Okay.
So it starts burning heavier atoms. And this goes on until you reach iron.
Okay.
And that is the point where fusion is no longer energetically creating energy. So it would take more energy to fuse the atoms than you would get out of the fusion.
Okay.
So at that point, well, the star pretty much dies. So it depending on its mass, it might actually, if it's not that massive, it will collapse, but something will happen that is very strange, which is that quantum mechanics will take over.
Of course.
Yes. And what happens exactly is that matter doesn't like to be in the same state. So if you take two particles of matter, of ordinary matter, there are two types of particles, fermions and I'm drawing a blank here. Oh shit. Anyway.
I got nothing.
So one kind one kind actually likes to, like photons, for example, like to be in the same state at the same time. And this is why lasers work, basically, because they like to all be in sync. And fermions, on the other hand, like the inverse. And this is due to their symmetry, to their fundamental symmetries. So it's not that they like or don't like, it's that they have to keep some symmetries, because there are quantities that are conserved, and you wouldn't be able to conserve them if you actually try to bring them closer.
Right.
And those symmetries are just there. You cannot escape them. They are mathematical constraints on the whole system.
Okay.
So the consequence of that is that all that matter has to take a certain space, because they cannot. Taking less space would mean that you would have two fermions in the same state, which is impossible.
Okay.
Mathematically impossible. So I said that quantum mechanics takes over. It's actually mathematics that takes over.
Okay. So is this where the collapse happens then?
So when that happens, you get a neutron star.
Oh, okay.
And then what happens when a star is even too massive for that is that you get a black hole. But I don't quite understand exactly what's going on. Okay. Especially with those mathematical symmetries, I don't know how they can go away.
Okay, so how about our own star? Do they suspect that one day, billions of years from now, that may turn into a black hole, or is that just going to die or turn into a neutron or something?
Our star?
Yeah, our own little star.
No, it's too small. It will never be a black hole.
Oh wow.
Yeah, it will just be a cold lump of
our little slacker star.
Yeah,
okay.
It won't even be a neutron star. It will be just, cinders.
Cinders, space cinders.
Yeah. It will just be relatively ordinary matter that will just cool down very, very slow.
Nylon, so we ain't going to be around for this. So there's that. Oh, and then the timing for this. So this does not happen overnight or in an instant, right? This takes hundreds of thousands, if not millions of years for a star to collapse, correct?
Yeah, it depends on the kind of star. If I remember correctly, so our star still has a few billion years ahead of it before it starts exploding. But supermassive blue star, I think only lives for a few million years, if I remember correctly, before it collapses and gives something else. Yeah. So, but the final stages of the collapse can actually go pretty quick, and because it can actually end up in a supernova.
Okay.
So one type of supernova is when a star collapses and the outer shells bounce on the inner layers, and just that is very energetic because all that matter has to reverse course.
Yeah, it's like
very
fireworks.
fast, and that acceleration creates very powerful radiation.
These are some very violent events.
Yeah.
Quite a show nature's putting on out there.
Yeah, and there are so many stars out there that it happens all the time.
All the time, yep. And we're seeing stuff that's actually happened, hundreds, thousands, not millions of years ago that we're just observing now because of light taking so long to travel, which is also fascinating as well.
Yep. Yeah, but we do observe supernovas all the time.
And those we can just directly see, correct?
Some we can directly, you mean with the telescope?
Whatever tools we're using. I'm sure we have more than telescopes.
Well, sometimes we see, they can happen in our galaxy. I don't know what the frequency of supernovas in our galaxy would be.
I guess we can't just kind of observe them all. It's a big place.
So yeah, usually what we see is that we see a galaxy, that we see the brightness of the galaxy change, and sometimes we can resolve it to a degree, but you can't. You see the light from the star. You see that something very bright happened, and you can look at the spectrum and so on. But I don't know what you mean actually by see it directly.
Well, I guess telescopes would be one way, or whatever kind of measuring devices we use to look at these things.
Yeah. Okay. You can observe the spectrum and
all that good stuff.
Yeah, and last time we talked about how we can use some of those to determine the distance of objects, their intrinsic brightness. So yeah, when the outer shells collide, and that creates some new atoms because it's such a violent phenomenon. And then some of those atoms are radioactive and decay very fast, and then we explained that last week. But it's interesting to note that the heavier atoms, so those that are after iron on the periodic table of elements, have to be created in one of those superviolent events. They cannot be created in stars because they cannot be the result of a fusion reaction.
Okay, yeah.
So yeah, anything heavier than, more complicated than iron comes from a supernova.
Interesting. And that's basically how all of our elements get formed, is through these kind of, stars being born and novas and all of that stuff. And the birth of the universe, of course. Yeah, and there has to be an explosion at some point, so that matter is spread in the universe and can eventually create accrete and create planets. Like the Mythbusters started the universe because there's the explosion, right? Yeah, they like explosions so much. But yeah, so the initial composition of the universe, and we know that to a high degree of certainty. We only had hydrogen, helium, some lithium, and the rest is traces. But mostly hydrogen. Which is so rare on Earth. Yeah. Well, actually, no. It's all in molecules. Let's say. Yeah, we have it. Okay, cool. Anything else, or? Stuff. Aren't bosons the opposite of the fermions? Yeah, that's the word. I don't know why that word just couldn't. Yeah. Yeah, that's weird. Yeah, fermions and bosons. Thank you. I'm surprised I could even remember that one, because I don't read up on that a lot.
Yeah, there were a few interesting things, such as the idea of a black hole was actually something that predated general relativity.
Oh, okay. So who proposed that?
Laplace and the other guy, John Michel. So they both made that prediction. The idea being that, it was a very counterintuitive idea that light, which doesn't have a mass, could be influenced by gravity. That was something that was not obvious at all. But when you do the calculations of the trajectory of an object in a gravitational field, in a Newtonian gravitational field, so you have on one side of the equation, you have mass times acceleration, okay, and on the other side, you have the gravitational force, right?
Yep.
So you have mass times the acceleration equals something, and that something is the product of the masses of the two objects, the gravitational constant, and the square of the radius of the distance between the objects. Okay. You have the mass of the object on both sides of the equation, so you can remove them, which means that the trajectory of the object only depends on the mass of the object you're rotating around.
Okay.
Which means that no matter how heavy you are, if you have a certain speed, you will follow the same trajectory, no matter what your mass is.
Okay.
So from that, you can ask, okay, what about light? That doesn't have a mass. So as mass tends to zero, the trajectory doesn't change. So you could conclude that light might actually do the same thing.
That sounds a little convenient, though.
Yeah, there is something that is not quite right with this reasoning, but because it pretty much says that the behavior of the limit is the limit of the behavior or something like that, which is a logical jump that is not entirely warranted. But those guys were happy to consider the option, and they happened to be right because, as we know now, gravitation is actually caused by space-time being curved,
right,
rather than by a force in the conventional sense. Yep. So light is affected by it just like anything else.
Well, plus there's the whole counterintuitive nature of science. I would say as much is counterintuitive as is not, as seems natural to us, if not more, actually.
Yeah,
especially once you start getting out into space and stuff like that.
But there was a logical jump here that wasn't warranted.
That was not right. Yeah, like, no, that doesn't sound.
But if you were willing to do that jump,
yeah,
which is a reasonable hypothesis, I mean, why not? Then you would conclude that the escape velocity, which is the minimum speed you must go to escape the gravitation of an object. So if you compute the escape velocity of an object, and that escape velocity is larger than the speed of light, you have a black hole.
Yeah.
You have a classical black hole, a non-relativistic black hole. Newtonian black hole.
Newtonian black hole. That's also a good band name, Newtonian black hole.
Yeah, everything in science would make good band names. Yeah.
Okay, so we're not going to have to worry about black holes doing any damage to us as humans in our lifetime, or our kids or grandchildren's lifetime, or any of that sort of thing. Except the advancement of science, that's about it. Like, we're not going to see any discernible effects on our lives from any of this.
Well,
or stars dying.
The probability is very, very low. But it could happen because, let's say, for example, that you had a stray black hole traveling through space.
Can that happen?
It could.
Okay.
Because, the gravitational field around a black hole is, I mean, a black hole is not something that is necessarily super strong
Right.
in
Well,
the
and
sense
I
that
guess they don't just sit there either, and they do always have stuff around them, right? Like the rest of the galaxy. So they would be traveling through.
not
But it could be
necessarily,
like a rogue one, just kind of zipping through there.
yeah.
Okay.
It's
I
not
guess
entirely impossible. And if
okay.
that were to happen, we wouldn't see it coming, probably.
Oh, damn. That'd be it. It'd just
Yeah,
be done. We're done.
yeah. So if you're interested in all those exotic end of the world scenarios,
Well, not that one. It happens too fast and there's no zombies. I mean, where's the challenge?
yeah, I don't see the point in that.
You know, I'm preparing for the zombie apocalypse. That one, you're just done. There's nothing, no challenge there.
Yeah, so let
There
me
are some
find
interesting doomsday scenarios around this stuff.
what do you mean?
Just like the fact that, a stray one could zip on through the neighborhood and then you're done, or something like that. Some kind of space event can happen. We might not see coming.
So I'm trying to find the title of the book because I don't remember it. What's the name of the royal astronomer in Great Britain? Martin Rees. Yeah, that's it. Martin Rees wrote a book about that. And the book is called Our Final Hour.
Okay.
And it's a very fun book. He's going through all those end of the world scenarios that are scientifically plausible, which doesn't mean necessarily that they are likely to happen.
Right.
So the probabilities might be small, but they could happen. And some of them are actually not that unlikely. So he talks about some of those, random crazy scenarios, but he also talks about some not so crazy scenarios that we seem to be heading for. Right. So it's a good book.
On a similar vein, Phil Plait, who goes by the Bad Astronomer, wrote a book called Death from the Sky.
Death from the Sky, yes.
And it's like the same kind of thing with these,
yes.
Some plausible, some not so plausible, but these different scenarios of what can happen.
All the ways the sky could kill us.
Yeah.
Yeah. One of the most likely would be an asteroid or a comet hitting the Earth.
Actually, you're more likely to get hit by a bus hitting you, but there's
sure,
but nonetheless, yeah, these kind of fun doomsday scenarios. Nobody wants to think about getting hit by the bus.
Yeah, probably not something you should be worried about, but
be more worried about the bus.
Well, some people actually worry about the asteroid scenario and are trying to do something about it.
True.
But yeah, you can go about your everyday life without worrying too much. Not about that, at least. Cool. Anything else? Or are we done with black holes?
I think we got all the important stuff about black holes.
You think? Oh, no, there is so much more.
Well, yeah, but...
Yeah, there is the thermodynamics of black holes. There is...
things that can be explained here in like an hour or so.
Yeah, I think...
like basically we discussed that, I think.
Yeah. We got some good info in there. Some of which is probably wrong.
Well, no matter what it is that you speak about today, it's going to be probably wrong at some point.
Yeah.
Right? Like everything that I learned in school is pretty much wrong. You got to go and relearn it. Not everything literally, I'm exaggerating obviously, but there is so much science that we had learned, history as well, other topics, that the facts have, come out differently. So
yeah. Well, and in the case of gravitation, we know that there is something wrong with it.
Yeah.
we need to put quantum mechanics into that. And quantum mechanics is also slightly wrong in the sense that it imagines space-time as being that immutable background, and that is wrong as well. So we know both are slightly wrong, at least.
Got some adjusting to do.
Yeah, I would bet that quantum mechanics is the rightest of the two, but
that's the endeavor of science, though. We keep flushing out those inaccuracies, and we keep refining and fine-tuning, and trying to get closer.
Yeah, and what's interesting is that we are actually able to do very useful stuff with something we know is slightly wrong.
Right. Yes.
And it's
predictions and still build on that with our knowledge.
It's accepting that you don't need to have some sort of absolute truth to actually do stuff, and that's probably something useful to think about.
Very useful in science, because if we didn't rely on that, we wouldn't really have a good modern society at all.
Yeah, and you might go, oh, well, science doesn't know anything for sure, but there is this little thing, which is that it is always connected to reality, and if you lose that connection to reality, then you don't have science. Right. So as XKCD so accurately says, it works, bitches.
Yes, science.
And that is what makes it valuable.
Yes. Practical.
Cool. I think that's as good a way to finish this as another. So this was another episode of Absolute Zero. I'm Bertrand. And we'll see you guys again next week.
Next week.
Bye-bye.